Hi, I'm Nicholas Dwork, and today I'm going to be talking about a fast variable density Poisson disk pattern generation algorithm. The property of the pattern is that it's random, but no 2 points are closer than a parameter r to each other. R can be a function of location. How do we create such a thing? Well, let's assume we have a parameter r, and we'll start by choosing one point at random. Now let's choose another point at random. And we'll compare the distance between these points to our parameter r. In this case, it's greater, so we'll keep it. We'll do it again with a new point, but now this new point must compare to both existing other points. It's larger than r in both directions, so we're fine. We'll consider a new point. This new point must compare to all 3 existing points. It turns out that one of these distances is too small, it's less than r, so this new point gets rejected. And we continue in this way until we fill up the space with a pattern. This is called the dart throwing algorithm, and the good news is that it works. It works for all variations of Poisson disk sampling patterns. The bad news, though, is that for each new point you have to compute distances to all other existing points. So this is a big O of n squared algorithm. A researcher named Bridson created a much faster algorithm. We have the same parameter r with the same bounded region, and what he did was divide up this region into a background grid. And the cell size of each grid point is such that the diagonal is the length of the parameter r. So let's say you know your point is located in this dark gray region. We only need to compare it against existing points in the light gray cells. And so this reduces the number of comparisons dramatically. How about generating the points? Well, we choose a point at random, like we did before. Then we choose a circle of radius r centered on that point. And we know that no valid points can be in that circle. And we choose a circle of 2r centered on the point, and we choose some number of points in the annulus between these 2 circles. We discard any points that are outside our region of interest, and then we go about evaluating each one of these candidate points one at a time. For this candidate point, we only need to consider existing points in the light gray cells, and indeed, the original point we selected is in one of these light gray cells, and we see that this new point is valid. Great. Let's try another of the candidate points. We compare against existing points in the nearby light gray cells, and we see that one of the points is too close, so this new candidate point is invalid. And we continue in that way until we've identified all of the valid points from within the annulus, and then we repeat the procedure until we've generated a Poisson disk sampling pattern. So that's the Bridson algorithm. Every point generated is added to an active list. Only points from the active list are used to generate new points. If an attempt is made to generate points from an active point, and none of the candidate points are valid, that source point is made inactive. Once there are no longer any active points, the algorithm is complete. This is a big O of n algorithm. It is lightning fast. The bad news, though, is that it cannot generate a variable density set of points, and that leads to the work presented here. We're going to assume that a minimum parameter value is known, and we're going to make a background grid where the diagonal has the length of this minimum parameter. And like the Bridson algorithm, we're going to take advantage of this active list. So in this simple example, I've divided my region of interest into 2 sections. To the left of this vertical line, the Poisson disk parameter is r over 2, and to the right, the Poisson disk parameter is r. I'm going to create a candidate point like before, and I have a background grid like before, but in this case, the diagonal of the grid elements is equal to the minimum parameter value, which is r over 2. And for this new point, we can see that only these cells that are shaded light gray could possibly contain points that conflict with this existing point. And what I'm going to do is push into each of these cells the index of this point that might possibly conflict with any points in those cells. Then we go about creating new points like before. We discard any points outside our region of interest and we consider a new candidate point. And we see that it could possibly conflict with the first point, so we evaluate the distance, and we see that it's valid. Then we go about identifying only those cells that this new point could possibly conflict with, and we push its index into each of those cells. And we go through the procedure again and again. For this point here, it's too close to the point 2, so we reject it. And off we go creating our Poisson disk sampling pattern, this time with variable density. So that's how this pattern was created. It was generated in 100 milliseconds with a CPU on a 2012 MacBook Pro. So here are several patterns for several different variable densities and directional variations. Even the densest pattern was made in less than 1/4 of a second. I welcome you to review our paper. Thank you for your attention.